Hello everyone and welcome back. Today we're going to be talking about 6 costly engineering drawing flaws that your engineering drawings might have. Whether you're an engineer, product manager, project owner, or the owner of a business that is producing and selling parts, this video is for you. And if you are tagging along and watch this video with me, you'll be able to identify some of the risks that exist in your drawing to help you prevent waste of money, waste of time, and waste of resources. Okay. Without any delay, let's get started. Okay, before we move on to more of the details of the topic of this video, I want to take a step back and look at step number 11 of the 17 steps of our ultimate product guide. So step number 11 is talking about production design. So the production design is the final design combination that you will use to actually build and manufacture your product. So production design is as part of the detailed design step in an engineering design process out of the book Engineering Design 5th edition by George E. Dieter and Linda Schmidt. So that's kind of, they have it as a single step, and we have it as step number 11 in our ultimate product design guide. More specifically, we are looking at step 11.1. This is step 11.1 is production design packet. Production design packet is essentially talking about product definition. So product definition is the description, documentation, and all of the details needed to recreate a product. So products and objects, they don't speak. They don't have written words on them. So you need to have a separate stack of documentation that helps you recreate this product just like you did before, maybe numerous times, maybe for mass production. We're going to be specifically looking at the production design drawings here in this video. So just so you know, and towards the end, I'll talk about the ultimate product design guide so you can see kind of where this thing plays a role in the entire big picture. Okay, let's take a second to look at figure 1.1 out of the engineering design book. If you're designing engineering drawings or making engineering drawings to find the complete product definition, you're somewhere in the product design stage of the design process. So on the x-axis here, we have time. So this is how much time it takes to create a product. And in the y-axis, we have how much money and effort it takes / commitment it takes to create a product. Now, inevitably, there is a minimum amount of effort and time needed to create a product. And in this book, in this figure, there are 2 approaches that have been highlighted here. So in approach number 1, where you spend a decent amount of time in your market development, like researching the market, understanding what kind of dynamics there are in the market and what kind of products would fit in it. So you spend a decent amount of time in there, and you spend a decent amount of time conceptualizing your design. So that is maybe doing concept iterations, consulting with different people, designers, and doing market analysis to see what kind of design would work. Once you understand what you need to build, you go into the product design stage. So this is where we as Bevel Edge come in. We help you design your product. Now this is, and it's a smooth transition, so relatively low effort in terms of time and cost spent on product design. And this is contingent on if you understand what the actual design needs to be. So since the product design is going to be straightforward based on the previous research, the manufacturing naturally will also be straightforward because requirements are known and understood. And then when the product launches here, there's going to be user feedback as the product is in use. And hopefully there will be very little changes we have to make based on user feedback. Now, on the flip side, here's an extreme opposite approach of that, where you kind of have an idea, but you don't really do a lot of research in the market, and you think your idea is going to be doing good no matter what. You spend little time conceptualizing and going through the pros and cons of a given design. And then what you'd have to do is probably spend the same decent amount of time doing the engineering design work. So that's kind of, so you have limited knowledge coming in. So you pretty much spend the same amount of time and money designing it. And you actually start spending the most amount of money in production. So because the design wasn't clear, requirements weren't clear, as you go into production, you've maybe missed some things, or that's just where you actually start spending your money in the production of the actual physical product. So then you launch a product, which happens on this line. and you immediately get customer feedback and customers are unsatisfied. So now you're forced to go back, reach back out to the engineer or the designer, make some changes, spend more money, do another rerun, which inevitably causes you to spend more time and money and effort on it. Now, one way or the other, you'll get to this point. Bevel Edge, we specialize in this section of the product design cycle. So this is just something to keep in mind. And of course, step number 11, especially step 11.1 in the product drawing stage, that's what we're talking about. And these are all part of the detailed design out of the engineering design book. So just so you know where we're at and how this fits in and why this stuff is important. Before we get further into the details of engineering drawing requirements and flaws that exist in them, I want to take a second and explain what engineering drawings are not. And here we're making a comparison to pattern illustrations compared to engineering drawings. Okay, and there's some bullet points listed here that will help you distinguish between them. So a pattern illustration is a publicly available drawing, essentially, or a figure. So whenever you publish your patent, these illustrations, the entire world can see when they look up your patent. Okay, versus a engineering drawing is proprietary and confidential. So nobody, unless they have explicit permission from you, are able to see these engineering drawings. So that is kind of a trade secret, and this is a intellectual property development that's public. Okay, a illustration patent or patent illustration explains what the idea is. Okay, it just tells you from a top level view, here's the idea, and this is kind of how it would embody itself. But an engineering drawing explains you how to build the idea. So what the idea is, how to build the idea. So the requirements, technical details are much more stringent for an engineering drawing, and that's listed here. So extensive technical details needed to replicate a specific part. And in a patent illustration, the technical detail is very minimal. Mostly it's just calls out individual parts and names them and how they relate to each other. And this is not really needed to recreate the product. This is just enough technical details to get the point of the invention across. Now, in all, a patent illustration is part of your intellectual property, but the engineering drawing is part of the development of technology. So a single patent can branch out into many different technologies, and these technologies are controlled by engineering drawings and CAD models. And that is kind of the difference between these two. Looking at figure 8.8 of the engineering design book by George Dieter and Linda Schmidt, you can see that engineering drawings have a cycle of development from conceptual to CAD to actual detailed design. And basically, first you come up with an idea and you sketch it by hand. Then you hand it over to a designer, and the designer creates a 3D model of the idea, the concept that you had. Then you convert that concept into engineering specified details. That way you can manufacture it. So as the engineering drawing is being developed, more and more detail is added, and that's kind of represented in figure 8.8. And more detail can be found in page 314 and in that same chapter. Now, I have worked with clients who do not understand the value of an engineering drawing, and I wanted to explicitly list out what the purpose of an engineering drawing is, and here are some bullet points. Now, there might be additional purposes or reasons why you want to have an engineering drawing, but these are, for the most part, the most important one. As we mentioned before, an engineering drawing provides details not captured in a CAD model. So you have these CAD models here on the right, and they show you the geometry, but maybe not necessarily some of the tolerances and how much wiggle room there exists. Maybe one part needs to be extremely accurate and the other part does not need to be so accurate, and the accuracy might affect your cost. That is also part of the deviations from the ideal geometry, right? So CAD models are ideal, drawings show you how much you can get away with from the ideal. Engineering drawings also serve as a universal language between the designer and the people manufacturing, and that's kind of summed up as design intent. So, maybe you are making your product out of China and they don't speak English. you just send them the engineering drawing with the additional details and the full product definition, and they will be able to interpret based off of the CAD model and the engineering drawing what to make. Now, this does not necessarily have to be a language barrier. This could also be that you might get a quote from the sales department of your manufacturer, and then it's a completely, and you have maybe an extensive conversation with the salesperson on what the details are that you want in your product. Then they get handed on over to the shop floor, and the people in the shop floor have not spoken to you, but they're given a drawing, and they will follow the drawing. So this is kind of another reason why you want to have engineering drawings, because the communication chain can get broken, and the engineering drawing carries that detail over to the last person responsible for implementing the actual details in your physical product. Okay. Engineering drawings are also used to quote parts, as we mentioned before. If you're discussing with a salesperson, depending on the details and tolerances needed, it will help you determine the manufacturing process of your part. So the manufacturing process used to make a part has a huge impact of the quote that you'll get back in terms of cost. So maybe you have to have something that's laser accurate. Then you're using a laser that's maybe super expensive to run, or your part needs to be welded, and those details would come to light looking after someone looks at the engineering drawings, and now you have to spend a lot of money on the welder. Or maybe based on the dimensions and tolerances that you have in your engineering drawing, the part can be stamped out, which is maybe super cheap to do, but it requires high amount of volume to reach that price point. So an engineering drawing will help get you the right quote and prevent misquotes in the future. Now, these last 2 points is kind of the whole purpose of this entire video. An engineering drawing establishes the obligation between the customer and manufacturer. So when you are paying your manufacturer $30,000, $40,000, $60,000 to make a run of a given part or a product, you want to make sure that you guys are on the same page and that mistakes don't happen, right? The worst thing that I could imagine in this scenario is that you've given the CAD model to them, and they give you what they thought was the interpretation of the tolerances and requirements of the surface of the CAD model, and this is not what you want. So now you have a big dispute on, hey, you didn't give me what I paid you for, and they can say, well, you didn't give me any of the details, so it was up to me to decide what's important and what's not important of your CAD model. So the engineering drawing kind of helps you in terms of litigation and finger pointing to see whose fault is what, and how we both, you and the manufacturer, can come to the same final product definition together. And then lastly, the engineering drawing helps protects the owner or seller of the product from claims and litigations. Let's say a part fails in the field, someone gets hurt, a product has a flaw, and you're sitting in court defending yourself why this product was good as is, and additional, and you can point to your engineering drawing, which is a documentation that you've been sharing with the manufacturer and the designer, and the details in the engineering drawing can help protect you, establish why your product was a good fit for production, and why the risk of that danger that happened or the malfunction that happened is not necessarily your fault, because the due diligence was explicitly stated in the drawings, so it couldn't have been you. And these are the most costly mistakes that exist in engineering drawings, and in the rest of this video we'll go through these. So here is a sample part that we've made only for the purpose of this video, and this is the drawing of that sample part. In the large space here, in this large blank space where you can see the CAD model and the actual views of the drawing, this section is controlled mostly for dimensioning and tolerancing of the specific part. Okay, and the sections highlighted here in the bottom, this is kind of called the title block of a drawing. This helps control the engineering drawing practices and processes. Okay, and the 6 listed mistakes are here on the side, and these 6 listed mistakes are highlighted here in the title block with the different color code. Okay, let's go through them. Drawing identification. Drawing identification usually happens in this red section, explicit notes. The explicit technical notes are here in purple. So here are some in the title block, and here are some notes that vary depending on the parts that you have. A explicit legal disclaimer that kind of helps control the legal value of this document with the manufacturer. And then also in green, the peer review process. So who has looked, checked, and approved the drawing that you have created. And you might also have a stamp of legal authority by a professional engineer on your drawing. And finally, the explicit design state in blue. So in blue here you have the explicit design state that is called out. That is mostly a communication between the client and the engineer. So it would be the client that comes to us and says, hey, make me and design me this part, and Bevel Edge puts this blue note in here, or this note design state of the drawing, to help communicate to the customer what state the drawing is in. So let's go through the details of all these all these 6 mistakes, and how you can prevent that in your engineering drawing, and what you can do in terms of reviewing your engineering drawings and making sure that you don't have these mistakes in there. All right. Now, if you're an engineer or an engineering student practicing engineering or wanting to learn it, there are 2 separate American Society of Mechanical Engineering standards, also known as ASME. These are part of Y14 standard set that define the engineering drawing related document practices. So Y14.5 is dimensioning and tolerancing, aka gd&t. That covers this section of an engineering drawing for the most part. And then Y14.100, this standard covers the highlighted sections that we just talked about previously. So this is worth mentioning, and an additional resource if you want to dive deep into those details. In this video, we're not going to dive that deep into the details and keep it surface level. Okay, before we move on, since we are talking about things that can be interpreted as legal advice or maybe financial advice, I want to take a second to explicitly read out these disclaimers that I have for the rest of this video. So this content is provided for informational purposes only, not as a substitute for professional legal counsel. And this content is provided for informational purpose only, not as a substitute for professional financial advice. Even though we do touch on some topics that are related to legal applications of engineering drawings and processes that discuss the financials of an engineering drawing, all of this is for informational purposes only. So if you are looking for quality consulting, you can reach out to a legal attorney or get financial advice from someone who's certified in that. Diving right in, let's zoom into the section highlighted in red of the title block. So that is a zoomed in version of what you have here. And this is part of the drawing identification. Now, why is drawing identification important? So drawing identification prevents the manufacturer from making and wasting thousands and thousands of dollars making you the wrong revision or the wrong part to begin with. Now, maybe parts look similar physically in the real world, but there are technical details that make them separate. So for example, maybe it's the same part, but it's for the left side compared to the right side, and they would have separate drawing numbers to help identify the changes or the differences between these. Drawing number changes in an engineering process usually notify changes in form, fit, or function. So if there is a part that looks like another one but has a different number, their form, fit, and function is different. So that's the first indicator to your manufacturer. And if you're making revisions to your drawing and you're changing the form, fit, or function, the drawing number will change. That way everyone is on the same page on what kind of part they're making. Now, the revision letter or revision number of an engineering drawing indicates minor changes in the details of the drawing. For example, maybe there was a dimension missing and we're adding that dimension. And when we add that dimension, we're just revising the rev number of the drawing. It didn't change form, fit, or function. It just changed it. Maybe there's a change the details inside of here. Maybe there's an extra view I want to show. Maybe I want to show you this side, the back side of this tube. So I'll add that, and that increases the revision of the drawing. So these are just minor changes. But in general, the identification of the drawing takes place and must be explicitly stated so people know what part they're making. There is room for a reference drawing maybe if this is the right hand side, this is the left hand side, you can explicitly state the reference to the different one. That way they're both listed so people know what the differences between them are, and if they don't know, they're tipped off to look at it. And also the document title, here highlighted in red. Of course, the document title is kind of the name, the human name for a given part. So these are just numbers that are in a computer system, but the actual human name will help you understand what the part is. So this one is called test piece created for test drawing. Okay. So this section of the title block that identifies who the owner of the drawing / technology is. Right, that could be very much different than the person who designed it. Just because you designed it doesn't mean you're the ultimate owner of it. So we explicitly state that in the drawing. So property of your company LLC. This is a fake company name that I've created, or a person's name that this drawing was made for. The reason why you want to state who the owner of the drawing is to separate the ownership of the technology between you and your manufacturer. If you don't explicitly state who owns the drawing, the manufacturer could just say, hey, maybe you've gifted this to me and I can make and produce as many of these parts that I want. But if you're explicitly stating, hey, this is mine, you can't use it. You have to come and talk to me before you want to use it. Or there's a dispute between the ownership between the person who designed it and the ownership between the person who is buying and selling these parts. So you want to explicitly state who owns this drawing, which goes back to who designed the part. Now, we here at Bevel Edge are proud of the design that we do, so we put our name on the drawing and identify ourselves. That way, if there are issues, if you cannot get into contact with the owner, you can come and reach out to us and we will help clarify information. So, since we are proud of the work that we do, we explicitly state who it's designed by and kind of help share some of the responsibility with the owner of the drawing. All right. Next is the mass call out in the identification. So maybe you have the same part made out of gold, the same part made out of silver, or the same part made out of cardboard. Geometrically, in the drawing, they look the same. However, by having a mass call out, you can kind of help distinguish between the two if that distinction isn't obvious to the manufacturer or the person reading the drawing right away. The mass call out also helps you with estimating of the cost and logistics of the product, right? So if the product is 200 pounds, maybe you need a forklift to move it, but if it's just 20 pounds, maybe someone can carry it by hand. So this is explicitly stated out in the drawing and will help for shipping cost estimation and handling estimation. Next is the drawing size call out. So why is that important? Well, all of our engineering drawings at Bevel Edge are 8.5 by 11 inches, and that is to make it easy for anyone to print it out with standard paper that they have. Now, sometimes a drawing can be printed, and maybe because it's a long drawing, part of it gets cropped out, okay? And in the cropped out part, there are a huge amount of technical details or critical details that were left out of the drawing. And this is why we want to explicitly state the size of the drawing. So if somebody prints it on the wrong size of paper and information is missing, they cannot use that as an excuse against you. Well, I didn't see it because his engineering drawing was a weird size and I had no idea what size the paper needed to be to print it. We explicitly tell you. And of course, the drawing scale to show you the scale size differences between what's on paper and what's happening in real life. So these are all helpful information and will help you protect you from future mistakes that are potentially making your product vulnerable. Okay, one last thing that's similar to drawing size is sheet number. Maybe the drawing has 4 sheets, and when someone prints it out as a copy, sheet number 4, the 4th page, goes missing. And they hand it over to someone else, and they are making and producing your part, and inevitably miss the details on page number 4, or maybe they purposely leave it out because it was too difficult to meet. And now you're sitting there with a bunch of product that has details missing that you explicitly wanted and paid for. So we just tell you this is sheet number 1 out of 1. So when physical copies are printed and handed, the reader of the drawings knows that there are maybe 4 sheets, 5 sheets, 6 sheets that need to be combined in order to get the full idea of what the drawing is trying to tell you. And this just kind of helps miscommunication or mistakes from happening in the field, and helps protect the owner of the drawing. Legal disclaimer between you, the manufacturer, or the person reading the drawing. Okay, so highlighted here in the bottom left corner in the yellow section, and it's zoomed in, this is the legal note that every engineering drawing should have, and if yours doesn't, you should probably review and reconsider that in your drawing. I'm going to go ahead and read this note out for you. That way it makes sense when we start talking about further details of why this note is needed. Okay. This document and its content are confidential and proprietary information of your company. This document may only be provided and used by persons outside of your company in regard to the terms and confidentiality agreement that explicitly cover this document and its content. Persons in possession of this document who do not have applicable confidentiality agreement with your company are directed to promptly return this physical or digital document to your company LLC and destroy any copies. Okay, so why is this needed? Well, first of all, it tips you off and the manufacturer off that there is a confidentiality agreement between the owner of this document and the people who are manufacturing this document. Your name, or the owner, is explicitly named here, and here it's just called your company. If you have a DBA, doing business as, you can list that here, and we also explicitly list the full name of the company as well. So there's no excuse between, oh, we didn't know they had a DBA as such and such. So those things are going to be listed here. And why is this legal note needed? Well, you could have a confidentiality agreement with your manufacturer, and we've signed an NDA, but they said, well, I didn't know this document you gave me, this drawing you gave me was part of the NDA. How am I supposed to know? Well, when your drawing has this note on it, it explicitly tells them, hey, this NDA that you signed, this drawing is part of it. And if you're manufacturing your part outside the United States, you might want to have an NNN, a non-disclosure agreement, non-complete agreement, and non-circumvention agreement. And this explicit legal note or legal disclaimer on your drawing helps tie your engineering drawings to those agreements that you had with your manufacturer, whether in the United States or outside the United States. And if you want to have, a more robust legal disclaimer, you ideally work with your attorney, and in your document or your legal agreement, you have a specific note written that matches exactly what is in your drawing. So in your legal agreement, it says, hey, if every time you see this note, then any document that has this note on here is part of this legal agreement that you've signed, and then this legal note that was agreed upon and signed on the dotted lines is explicitly stated in your drawing. So that is one way you can protect yourself from people copying your product, and this is one way you can prevent disaster and waste of money in the future. Okay, next, highlighted here in purple are the explicit notes of any engineering drawing. So these explicit notes usually help with the controls of form, fit, and function of the part. So additional details that are not dimensionally defined, but still help with form, fit, and function of the part. And this cross-sectional view right here is zoomed in and shown. And here are some of the general notes that we have. So let's dive into what these notes are and how they work to help protect you as the owner of a drawing. Okay, the explicit variable notes that are listed here outside a title block are notes that can continuously change. So these could be details such as, hey, use this specific torque wrench whenever you're assembling my product. Use this specific lubricant whenever you're assembling these parts and whenever these parts are touching. So some of these details, or hey, if you're using something that is of a certain tolerance or a certain product that is off the shelf, make sure it is this kind. So those are the notes that are explicitly called out inside the drawing, the blank space here, outside the title block, and are variable from individual drawing to drawing. So these can change at fly, versus where the things in here usually stay constant and the same. Okay, so the first one, surface finish. So if the surface finish, I guess let me read this here, unless otherwise specified. So that just means this applies to the entire drawing unless I tell you otherwise up here. Surface finish of roughness of 250, square root of 250. Okay, now the manufacturer maybe made your part and the outside of it looks like this, and that's not what you wanted. You want it to look smooth, maybe somewhere between here and here, which is a 250 that we've called out as a default. And now you're sitting in a dilemma of, hey, all these parts you've made, all that money I've gave you is now wasted because this is not what I want. And they can argue and say, well, you didn't tell me what surface roughness you want. It was up for me to interpret, and this was the cheapest option for me. But if you have it called out explicitly, that helps you protect from this mistake and this dispute from happening in the first place. Or if the dispute does happen, you're protected by the explicit call out. Okay, next. Do not scale drawing. Just because I have a certain ratio of dimensions pointed out here doesn't mean that if you just make it bigger, it will work for a bigger system. Or if you shrink it, it will still work the same way. Now, for a cup, a sippy cup or a coffee cup, these things might be true. You could simply just make everything larger in proportion to one another, and the function still remains the same up to a certain point. But certain engineering drawings cannot do that. Maybe if you make it 20% larger, the weakest point of the part transfers from one location to the other, and disaster can happen. So it's also important to note this out. If your manufacturer was like, well, you just said you wanted something that's a little bit bigger and I made it bigger for you, and what do you know, now something fails. So this protects you and the engineer and the design team from these issues from happening in the first place. Okay, next, inside and outside corners are radius of 5,000 or chamfer of 5,000 by 45. And the engineering model, so the CAD model that you see, will naturally show perfect round sharp corners. The engineering model will show perfect sharp corners, and these sharp corners in the real world could injure people. So you're just saying, hey, I know in my model everything is perfectly sharp, even though it's like also shown in my drawing. But what I want you to do is go and take care of those sharp corners. And the inside corners, like any tool that you use to machine an inside corner, will have a natural radius. A perfect 90-degree sharp corner does not exist. The further you zoom in, the more of a radius you will see. And you're just saying that this is kind of the general size of an inside sharp corner that you want. Okay, next, remove all sharp corners and burrs. So the argument can be made that in note number 3, I've chamfered all these corners so they can come in and make these corners 45, but there are still these burrs that exist, especially if they're cutting threads. And these are not shown in the drawing or in the model, but they happen during the manufacturing process. So what you're telling them is that, look, even though this happens, even though maybe your dimension is perfect and your chamfers are right, I still want you to go and deburr these, because this is a legal liability. Like, people can get hurt if the parts reach the customer, someone cuts their finger, God forbid they hurt their eye, or even the people in the shop are handling this product, they also could get hurt or cut. So you're telling them, please take care of that, and it's explicitly stated. Okay, next. We're telling the manufacturer, the people reading the design, that we have a specific standard of the language of the drawing that we are following. We are following ASME 14.5 and we're following ASME 14.41. So 14.41 is for the CAD model that you're giving them, so the digital product definition. And then ASME 14.5 is for the dimensioning and tolerance scheme that you send out here. Now, these dimensions can be interpreted depending on which standard you follow in a different way. And you're telling them, look, this is the standard that I followed when I designed it, and you need to interpret it as such. And if you want to convert it into a different interpretation, know that this is the base truth. And this will set off the requirements for the rest of the notes that are coming up. Okay, you also want to tell the manufacturer explicitly that the dimensions that you're creating need to still be true after painting and coating. So maybe you don't have explicitly stated how many layers of coat of paint, how many layers of primer versus the final paint, what the thickness of anodization needs to be. And here you're telling them that no matter what the surface coating is, I still want these dimensions to be true so that things can fit together. Now here's a pipe flange, for example, and it looks like it has a thick coat of corrosion resistant paint on it. Now just imagine if the thick paint would make the through holes for these bolts small to where these bolts wouldn't fit through. What would happen next is someone would go and drill them out, damage the paint, and create a position where corrosion can start again because the paint is missing. So you want to prevent that from happening in the first place, and it's explicitly called out in the drawing. Okay, lastly, here is the large chunk of the last notes. These go back to the ASMEY 14.5, this section here, and kind of help refine and reinterpret some of the dimensional details that we're looking for. I'm going to read these out for you. Drawing is not fully dimensioned. Okay, so this drawing is not fully dimensioned. All drawings do not exist. So if there's something missing, it wasn't omitted. It was intentionally, it wasn't forgotten. It was intentionally omitted. And now you're telling them obtain all undimensioned values from respective model. So you're giving them a drawing that has dimensions missing, and you're telling them if their dimension is missing, go to the model and measure it. That goes part of your product definition as the full design package. So you need to have the model and the drawing to interpret what the full geometry is. And the question is, why would you not want to fully dimension your drawing? And the reason for that is simply it can get cluttered, and it's a lot of extra work and a lot of extra cost. So to prevent clutterness and misinterpretation, like you see here, you omit some of these drawings and tell them to go and find those from the CAD model, and that allows you to explicitly state the critical dimensions. Okay, all model dimensions are in inches, so the drawing is in inches, so all your model dimensions should also be in inches. All model dimensions to be interpreted as basic with 3 decimal places, so maybe they go in and measure a certain distance and it has like 7 or 5 decimal places, or they just round it up to 1 decimal place, but you're telling them, hey, can you please go and round it up to 3 decimal places? Do not lose any dimensional detail by rounding it, and you telling them exactly how far to round your dimensions in the model. So this will help you in the future from mistakes from happening. Next, number 11, drawing is authority for dimensions specified in drawing. 12, model is authority for dimensions obtained from the model with all surfaces, the 30,000 profile to A, B, and C, datums A, B, and C. Okay, why is 11 and 12 explicitly stated? Well, you're inevitably given the interpreter of the drawing two sets of dimensions. So when they're looking at this, they're seeing this tolerance, and then if they look at the model, they find that same part and go and measure it, and now you've told them that the tolerance of that is based off of 3 decimal places to this. So you're giving them 2 different sets of tolerances for the same feature. And here with number 11, you're telling them, look, if I have it called out explicitly in the drawing, that overrides anything you see in the model. And if it's not in the drawing, you can go see the model, and here are the general tolerances of the model. So this is pretty technical, highly technical, and it needs to be clearly stated here to help protect you from misinterpretations of the complete product design package and the product definition. So if your title block or your drawing has these notes missing or are unclear or contradictory, you want to go and review those to prevent further waste of money and future waste of time from happening. Lastly, unless otherwise specified, are the machining tolerances called out and the fabrication tolerances called out. So depending on the requirements of your part, you could either make it by hand, aka fabricate it with looser tolerances, or you're forced to machine it with a CNC where you get extremely accurate dimensions, and here are the tolerances called out based off the number of decimal points. Now, this in turn helps you reduce clutter and misinterpretation in your drawing numbers. So if you have a dimension called out with 2 decimal places, for example here, then the reader will go and see it's 2 decimal places. So this is the interpreted tolerance for that. Now, if there's something that has 3 decimal places and no tolerance called out, you can come down here and find the exact tolerance, which is more accurate. So the reason why these general tolerance notes are separated is to prevent clutter, and 2 versions exist to allow for variable different manufacturing approaches, whether it's machining or fabrication. Here we're talking about the green highlighted section of the engineering drawing title block and drawing surface, and this is about peer review and legal authority. So every engineering design has inherent risk to it. It poses maybe physical or chemical risk to the user, and you want to make sure that the design has been reviewed by multiple competent people to catch any mistakes before sending it to production. And in our drawing template here at Bevel Edge, we have 3 levels of checkers. One is the designer. Here it's Joseph Smith. And then you have the checker, Kevin Gates, and the respective date which the designs were pushed forward and checked respectively. And then you also have the final approver, the person that has the final approval to push a drawing from prototype stage to production, and here in this case is John Doe. So, and here is when he signed it. If you have a drawing that has not been peer reviewed with people's names as a sign off, then you are maybe liable to some of the risks that this product could create. So maybe it malfunctions or someone gets hurt, then it comes back to you and they say, hey, you are the owner of this drawing, you're the company that's making and selling these parts, who reviewed this? And if you don't have names to point to, you are not sharing the responsibility. It is 100% on you. And then also the ultimate legal authority with a professional engineering stamp. An example here from Texas, since we are based out of Texas, is here. And an engineering drawing that has a stamp on it is accompanied with legal authority by the person who has put their name and stamp on it. So if an engineering drawing has a stamp on it, the responsibilities of form, fit, and function most of the time go back to the actual engineer who finally approved it. Next, let's look at the section in blue. This is the design state of a drawing. So this is explicit design state. That is a communication between the designer, engineer, or whoever is making the drawing and the final owner of the drawing. So if someone comes to Bevel Edge, for example, and says, hey, make me these parts, we will take the part design through design stages. So initially a part is in design stage. And this design state means that, you know, it's a work in progress. Nothing is defined, nothing is serious. And then as the product gets more refined and the details get together, you want to start prototyping it. So a prototype drawing is certainly a little bit more defined and more detail is added to make sure the prototype works well. However, a prototype drawing is not final and shouldn't be interpreted as such. The only drawing that's actually final is a drawing in production state. That means it has been approved and peer reviewed, and now mass manufacturing can begin, and the liability and the cost of the design can be shared with the people designing the product for you. Okay, let me read this note out and we can discuss it in more detail. Documents in design state, document in design state are incomplete and not fit for any production. So if you look at the drawing and you see this, that means do not make or build this part. Things are subject to change or are not fully refined and calculations haven't been completed. Now, if you find a document that is in prototype stage, let's continue reading this. Documents in prototype design state are only approved for prototyping and testing. So here, the engineer or the design team is telling you, okay, you can make this part, but don't make a ton of them. There are still outstanding questions. You can only build this for prototyping purposes only, to gather more data. Now, lastly, only documents in production design state are approved for full-scale production. So that means that prototyping has been done, calculations have been done, discussions have been made, and what we think is on this drawing is now fully approved for mass production, and you can make it and also sell it. Here in the bottom in this window, the design state is again explicitly stated in addition to the general note. So this section here will change from production, design, or prototype stage. So this basically helps communicate between the design and engineering team and the final user owner of this design drawing. So this is also something important to keep in mind, and for patrons who people who commission Bevel Edge to understand. Okay, now zooming back out to the entire sample drawings, we've discussed the title block requirements down here and discussed each individual section of this title block and how mistakes in this area or things that are omitted in this area could be costly for you in the future, and you should probably go back and revise and review your drawings and make sure that these exist. And if you have any questions on if your drawing is at risk, you can always share them with us with an NDA and we'll review them for you. So today's discussion was a small section of production design drawing requirements, and that is overall part of step number 11 of the Ultimate Product Development Guide. Now, we at Bevel Edge uses Ultimate Product Development Guide to help our clients build the ultimate product that is successful in the market with the least amount of risk as possible. This Ultimate Product Development Guide is free to download on our website. It helps you get a top level view of the 17 different steps that you need to make, all the way from product idea to design support, that will help make a successful product. Okay, with all that said, thank you very much for your time and hope to see you in the next video.